am Professor Manisha Pal from the Department of Statistics of Calcutta University. I am going to talk on design of mixture experiments. To start with, let us look at a mixture. What do you mean by a mixture? Well, a mixture is formed by blending or mixing two or more components or ingredients that do not interact chemically. Some common examples of mixture are construction concrete, which is a mixture of sand, water and cement. Then we have the fruit punch, which is a mixture of fruit juices, railway flares, which is a blending of magnesium, sodium nitrate and so on. Then we have the fertilizer mixture, which is a mixture of potash, rock phosphate, superphosphate and urea. And we have the cake mix, which will be a blend of baking powder, shortening flour, sugar and water. Any manufacturer of a product, he will be interested in one or more properties of the end product. For example, if we consider construction concrete, then the hardness or compression strength, that will be the property of interest. For fruit punch, the property of interest would be the fruitiness flavor of the punch. Then for railway flares, it will be the illumination and duration of the illumination. For fertilizer mix, it is the crop yield, and for cake formulation, it is the fluffiness of the cake or the layered look of the cake, and of course, the taste of the cake. Now, the final product that we get after mixing a number of ingredients, that will depend on the mixing proportions of the ingredients that have been used. So, it is important to study the relationship, the functional relationship between the property or properties which we call the response and the mixing proportions of the ingredients. Now, why do we make such a study? These are for two important reasons. Firstly, we have that from such a study, we get a better understanding of the effect of the different ingredients on the response. And secondly, we can use this relationship to determine the optimum mixing proportions that will give the best response. Here, response is the measured property in which the interest lies. Now, let us look at a mixture experiment. What is a mixture experiment? It is an experiment in which the response depends on the proportions of the ingredients being used. Now, any proportion, as we know, is a fraction that lies between 0 and 1, and if we take the sum of the proportions of the different ingredients being used, that is going to be 1, and this is a natural constraint of mixture experiments, and this constraint sets the mixture experiment apart from other experiments. It puts the mixture experiment in a class of its own. Now, let us look at the mixing proportions. Suppose we have a q component mixture and the mixing proportions are x1, x2 to xq. As I have said, each of the proportions, that is xi's, will lie between 0 and 1 and they sum up to 1. So, the experimental region, that is the region in which we consider all the possible mixing proportions, that will be of this form, that is x1, x2, xq. These denote the mixing proportions of the components, and each xi is greater than or equal to 0, such that sum of the xi's is 1. Because sum of the xi's is 1 and xi's are all greater than or equal to 0, it automatically means that these xi's will be less than or equal to 1. So, this gives the experimental region. Now, before we go further, let us look at the applications of mixture experiment. This mixture experiments, they have vast application in different areas of research and also in industries. For example, in agriculture, engineering, pharmaceutical, biomedical, horticulture, paint industry, food industry, etc., etc. Now, let us look at the geometric representation of the experimental region that I have just talked about. Geometrically, the experimental region defines a q minus 1 dimensional simplex when we are considering a mixture of q components. Then the question arises, why is it q minus 1 dimensional? That is because of the constraint that sum of the mixing proportions will be equal to 1, and all the experimental points that will lie inside this simplex or on this simplex. Now, the points that are on the vertices of the simplex region, they will be of the form 1 0 0 0, that is, we are using the first component or the first ingredient and not the others. Similarly, it could be 0 1 0 0 0 and so on. Okay, and such points are called pure or single component mixture, and they are also known as the extreme points of the experimental region. Now, the midpoints of the edges of the experimental region, that is given by half half 0 0 0. That means two of the components will be in the proportions half half and the other components are not going to be used. Similarly, it could be half 0 0 0 0 and so on. And there is another point which is of importance, that is the overall centroid point. The overall centroid point of the experimental region is a point where the mixing proportions are all equal. We are considering a q component mixture, so the mixing proportions will be equal to 1 by q. Let us look at the experimental region for a 2 component mixture. We have a mixture of 2 components with the mixing proportions x1 and x2, and x1 x2 lie between 0 and 1 and they sum up to 1. So, if I take x1 along the x axis and x2 along the y axis, then this line joining the point 0 1 to 1 0, this gives the experimental region. All the points on this will belong to the experimental region. Now, these 2 extreme points are the vertices of the experimental region, and half half, that is the midpoint of this line, that is the midpoint of the edge. Consider a 3 component mixture. The mixing proportions are x1, x2 and x3. They all lie between 0 and 1 and they sum up to 1. In this case, the experimental region can be, or the simplex can be represented by an equilateral triangle. The vertices of this triangle are 1 0 0 0 1 0 0 0 1. Along this line, that is between 1 0 0 and 0 1 0, you note that x3 is equal to 0. Along this line, that is 0 1 0 to 0 0 1, here x1 is 0. Along this line, we have x2 is 0. So, these are the vertices of the simplex, and the midpoints of the sides, which are the edges, are half half 0 half 0 half 0 half half. So, these are the midpoints of the edges, and the overall centroid point is inside the simplex, that is 1/3 1/3 1/3. If we consider, say, a 4 component mixture, in this case the diagram will be more complicated. Now, let us look at the response function. What do you mean by the response function? That is going to define the response as a function of the mixing proportions. So, suppose we have a q component mixture with the mixing proportions x1 x2 to xq, and let us denote these mixing proportions by x. Now, by capital Yx, I am denoting the response corresponding to the mixture blend x. Now, Sheffe in 1958, he was the first one to define mixture models of different degree as functions of the mixing proportions of the ingredients. That is, the response has been expressed in these models as functions of the mixing proportions of the ingredients. These are Sheffe's model. The simplest one is linear homogeneous model, where Yx is expressed as a linear function of xi's. But besides this, we have a term epsilon. This epsilon is the error term. summation beta I xi, that denotes the expected response. Yx is the true response. So, naturally there is going to be a difference, there may be, I should say, a difference between the actual response and the expected response, and that error is denoted by epsilon. Similarly, we can have the quadratic model where Yx is represented in terms of the mixing proportions this way. Here xi, xj, these are the interaction terms. Now, this quadratic model, I should mention, is the most commonly used mixture model. Then we have the full cubic model and the special cubic model. Now, in each of these models, we have the error epsilon, which is assumed to have mean 0 and the variance sigma square. That is constant variance, that is, we assume homoscedasticity. In these models, there is one thing that we note is that there is no intercept. Generally, say we consider a linear function, then that will be, say, y equal to a plus bx, where a is the intercept. But here in the mixture models, there is no intercept. Why? Well, this is because of the natural constraint that sum of the mixing proportions is going to be equal to 1. For example, if I consider the linear homogeneous model, it is of this form. Now, because summation xi is 1, I can multiply beta naught by summation xi, and if I do so, what do I get? I get Yx is summation beta I star xi plus epsilon, where beta I star will be beta naught plus beta I for all I lying between 1 to q. So, even if I take the intercept, I can reduce the model to this model where there is no intercept. Now, this constraint summation xi equal to 1 is a magical one. Why? Firstly, as we have seen, it helps to get rid of the intercept. Secondly, we can convert any function of any degree to a function of a different form, but of the same degree. For example, suppose I consider the quadratic model. Now, summation xi equal to 1, that can be used to convert a function of any degree to a function of a different form, but of the same degree. For example, if we consider the quadratic model, in this case, if I multiply the first term, that is summation beta I xi by summation xi, we can do it because summation xi is equal to 1. Then we get an expression of this form. The model becomes this, that is Yx equal to this form. Now, this form is very useful when we want to find the optimum mixture combination that optimizes the response. Now, we can also convert a function to a function of a higher degree using summation xi equal to 1. For example, suppose we have the linear model, then by multiplying summation beta I xi by summation xi, we can move on to the quadratic model. By multiplying summation beta I xi by summation xi square, we can move on to the cubic model, and so on. Again, if I consider the quadratic model, from there I can move on to cubic model, biquadratic model, and so on. However, when changing the degree of the model by using this identity summation xi equal to 1, one has to be very careful, because this may lead to remodeling very deceptively. The natural question that arises is, why should we conduct a mixture experiment? Now, we conduct the mixture experiment firstly to test whether the model that we are fitting to our data, that is a response data, that really fits the data or not. Secondly, we want to estimate the parameters of the fitted model. Once we are ensured that this model is the best model, then we have to estimate the parameters. For that also we need a mixture experiment. Thirdly, we may want to estimate some complicated, say, nonlinear function of the parameters. In that case also we need to conduct a mixture experiment. Now, let us look at design of mixture experiment. There are two commonly used designs of mixture experiments. So, the two commonly used designs are the simplex lattice design and the simplex centroid design. Now, each of these designs, they will be used for a different purpose. For example, let us consider the simplex lattice design. When the number of components is not very large, but we are using a high order polynomial to represent the response function, in that case we prefer simplex lattice design. And for simplex centroid design, if the number of components in the mixture is very large, the first choice would be to screen out the important ones. For this purpose, we use the simplex centroid design. Now, let us discuss the simplex lattice design. A QM simplex lattice design for a Q component mixture that consists of points which are defined by the coordinates as follows. Now, each of the proportions will assume the values 0, 1 by m, 2 by m, so on to 1. That is, each of the proportions take m plus 1 equally spaced values. The design space in this case will be all those combinations of proportions which are reasonable. Reasonable in the sense that they sum up to 1. Now, each reasonable combination of proportions defined is called a support point or a design point, and the m that we have used over here, that is called the degree of the lattice. So, it will be easy to understand if we consider some examples. Suppose we consider the 3-2 simplex lattice design. The 3 first over here, that denotes the number of components in the mixture. So, it is a 3 component mixture, and m, the degree of the lattice, that is 2 over here. So, each of the proportions xi, they can take the values 0, 1 by m, which is half, and 1. And the design space in that case is going to have 6 support points or design points. They will be 1 0 0 0 1 0 0 0 1, then half of 0 and its permutations. This is because we have to keep in mind that the sum of the mixing proportions is equal to 1. So, we can't have 1 over here and a half over here, we can't have that. Now, let us consider a 3-3 simplex lattice design. So, it is a 3 component design and the degree of the lattice is, or order of the lattice is 3. So, xi's will take the value 0, 1/3, 2/3, 1. So, in this case there will be 10 design points. We have the first are the vertices, that is 1 0 0 0 1 0 0 0 1. Then we have design points of the form 1/3, 2/3, 0, 1/3, 0, 2/3, and so on. And the last one will be the overall centroid point, that is 1/3, 1/3, 1/3. Now, one thing I should mention over here is that here in this case, that is 3-2 simplex lattice design, we are getting 6 support points. Now, from 6 support points, if we conduct an experiment at those 6 support points, we will get 6 values of the response. Now, from the 6 values of the response, we can at most estimate 6 parameters, and we have noted that if we we can go back and see that if we consider the quadratic model, where the number of components is 3, there are 6 parameters involved in the model. So, in a quadratic mixture model, we see that when there are 3 components being used in the mixture, then the number of parameters involved is going to be 6, and therefore, this design would be appropriate in that situation. It can also be used for the linear model, where there are number of parameters equal to 3. Now, let us come to the simplex centroid design. In a simplex centroid design, any design point, if we consider, then the non-zero elements of that design point, they are going to be all equal. So, the support points of a simplex centroid design for a 3 component mixture will be of this form. Here there is just one non-zero element. So, because of the restriction summation xi equal to 1, that non-zero element has to be 1. In this case, there are 2 non-zero elements. So, since the non-zero elements have to be equal, so they must be equal to half of. So, these are the 3 points which are the midpoints of the edges. And thirdly, if all the 3 proportions are non-zero, in this case each will be equal to 1/3. Now, how to plan a mixture experiment? Firstly, one has to be clear about the objective and the problem statement. Secondly, one has to select the mixture components, the ingredients of the mixture. Next, one has to identify the property or the properties of interest, which are the response variables. Next, one has to decide upon the appropriate model to be fitted and choose an appropriate design to conduct the mixture experiment. Once the mixture experiment is performed with the design points that have been selected or the design that has been selected, the data that is received, that is analyzed, and then one draws conclusions from this analysis and makes recommendations. Now, how do you specify a design? Now, suppose we consider a design xi, say it has support points. See, these are given by x bracketed 1, x bracketed 2 to x bracketed k. Suppose it is said that the design has to be replicated capital N times. Then each of these points would be replicated a number of times, like x1 is replicated n1 times, x2 n2 times, and xk nk times, and the sum of these replications should be equal to capital N, the total number of replications of the experiment. Such a design defined by xi is called an exact design. Now, the underlying assumptions that we make is: 1, response is being expressed solely by the mixing proportions of the ingredients. We are not using the amount of mixture over here. And the error terms, these are normally independently distributed with mean 0 and a constant variance. That is, we are assuming homoscedasticity. Now, the general representation of a response function. Now, generally speaking, we represent the response function as yx equal to f prime x theta plus the error term. What is theta? Theta denotes the vector of the model parameters. For example, if I take Sheffield's linear model, then theta will be beta 1, beta 2 to beta q for a q component mixture, and f prime x, that is the vector of the coefficients of the parameters, that is coefficients of beta 1, beta 2 to beta q. So, they come out to be x1, x2 to xq. Similarly, in Sheffield's quadratic model, these are the parameters, that is the elements of theta, and f prime x will be the coefficients of those parameters. Now, xi's, as I have mentioned, are the support points of the design xi, and by using a design point and carrying out the experiment, we get a response. Now, if we write down all the responses, we get the response vector. So, I am denoting by capital Y the response vector. Now, the estimator of theta, that is the vector of parameters, is given by this, where x xi, which is called the design matrix, is of this form, that is, I am writing down f x1 n1 times. That is because x1 has been replicated n1 times, f x2 n2 times, and so on, and this is the design matrix. Now, the information matrix from this, by using, rather I should say, by using the design xi, is 1 by sigma square x xi prime x xi, and the dispersion matrix of theta hat is given by the inverse of the information matrix. For simplicity's sake, we take the sigma square to be equal to 1. Now, suppose we want to compare two designs. We have conducted two mixture experiments using two designs. Now, in that case, there should be some way of comparing them in order to find out which one is better than the other one. So, in that case, for comparison basis, we consider the information matrix on a per observation basis. Like if I have xi as my design, I consider m star xi, which is 1 by sigma square xi prime xi divided by n. This part, apart from capital N, that is the information matrix of xi, that divided by n gives me the information matrix on a per observation basis. Now, for these two designs xi1 and xi2, I can calculate m star xi1 and m star xi2. If I find that m star xi1 minus m star xi2, that is positive definite, that means the information contained by using design xi1 is more than that when we are using design xi2. So, naturally xi1 is a better design. There is of course more to design of mixture experiments, but for now we stop over here. These are the important references: Sheffield's 1958 and 1963 papers, and for an explicit idea about experiments with mixture, one can look up Cornell. Thank you.